Titan is a moon that sits more than 1 billion kilometers away from Earth, spinning around Saturn in the cold darkness of space. When space probes arrived there, scientists discovered something that changed everything. Titan has lakes, rivers and rain, just like our planet. But it turns out those lakes are not made of water. They're made of a liquid so cold that it would freeze any human being in seconds. The temperature there is almost 200 degrees below zero, and the air is so thick that you would feel like you were underwater. Even so, many people dream of building homes and cities in this strange place. Will humanity ever manage to live in a world so different from our own? Get ready to fall asleep while listening to this video. Subscribe to the channel, leave your like and comment where in the world you're watching from. Get comfortable and relax. Let's begin. Imagine standing on the shore of an alien sea, but the waves are not water, they are liquid methane. And the air is so cold it would freeze your breath into icy dust before you could even exhale. That is the reality of Titan, and the very first thing any colonist would have to conquer is the cold, a deep, penetrating and unrelenting cold that defines every single aspect of existence there. The average surface temperature on Titan is a staggering minus 179 degrees Celsius. To put that in a more familiar perspective, the coldest temperature ever recorded on Earth was in Antarctica at around minus 90 degrees, and that was an extreme event. On Titan, minus 179 is a lovely average day. This isn't just a weather pattern, it is the permanent, unyielding state of the environment. This profound cold is the single greatest filter for every piece of technology, every material, and every human aspiration on that world. It is not an obstacle to be overcome once, but a constant, silent enemy that must be fought every second of every day. The challenge begins with the most fundamental element of any endeavour, the stuff things are made of. Our everyday materials, the metals and plastics and composites we build our world with, have no idea how to behave under such conditions. On Earth, metals are strong and malleable. They bend and twist under stress. At Titan's surface temperatures, many metals undergo a dramatic transition and become brittle. Imagine a wrench, a simple steel wrench left outside in that cold. If you tried to turn a bolt with it instead of applying torque, the wrench might just snap in your hand like a piece of hard candy. The molecular structure changes, losing its ductility. Aluminum, commonly used in aerospace for its lightweight, also suffers. Plastics and polymers, which provide insulation and flexibility, face a worse fate. They lose their plasticity entirely, becoming glass-like and prone to shattering. Rubber seals and gaskets, which keep air inside habitats and rovers, would harden and contract, potentially cracking and creating catastrophic leaks. Even specialised lubricants, the lifeblood of any moving part, would freeze solid. A simple hinge on an exterior door, a wheel bearing on a rover, or the joints of a robotic arm would all seize up, ground to a halt by friction and solidified grease. This means that every single component for a colony, from the largest habitat module to the smallest bolt, cannot be something we pick from a terrestrial catalogue. It necessitates a complete re-engineering of material science. We would need to develop entirely new alloys, novel composites, and base materials specifically designed to retain their necessary properties in a cryogenic deep freeze. Perhaps we would turn to the materials Titan itself provides, like water ice, which at those temperatures has the structural strength of granite. But working with ice as a primary building material brings its own set of incredible complexities, so you cannot use normal stuff. But let's say you solve the material science puzzle. You have a magical alloy that stays strong and a polymer that stays flexible. Now you have to build a place for humans to live, a bubble of warmth in that immense cold. The engineering challenge of thermal management here is almost incomprehensible. On Earth, our homes lose heat to a cold night, maybe down to freezing. The temperature difference between the inside of your house and the outside on a winter night might be 30 or 40 degrees Celsius. On Titan, the difference between a habitable interior, say a comfortable 20 degrees Celsius, and the outside environment is nearly 200 degrees. That is a thermal gradient so steep it is like trying to hold a single match warm in the heart of a blizzard. The heat inside a Titan habitat would be screaming to escape, rushing outward with relentless pressure. The insulation required is not just a layer of fiberglass in the walls. It would need to be a multi-layered, incredibly advanced system, likely incorporating vacuum gaps, reflective layers, and novel insulating aerogels many meters thick. Any weak point, Any thermal bridge where conductive material connects the inner wall to the outer shell would become a raging river of heat loss, causing the exterior to possibly melt the surrounding ice. Or, worse, creating a cold spot inside where moisture from human breath would freeze instantly into accumulating frost. And generating that heat in the first place is another monumental task. With sunlight 100 times dimmer than on Earth and filtered through a thick orange haze, solar power on the surface is virtually useless. The primary source of energy would have to be nuclear, either radioisotope thermoelectric generators for smaller outposts or full-scale fission reactors for a colony. These reactors would not just provide electricity for lights and computers. Their most critical function would be generating the sheer thermal energy needed to keep human beings from freezing to death in a matter of minutes. The loss of power is not an inconvenience on Titan, it is an immediate colony-ending event. The systems would need immense redundancy, but a habitat is not just a warm box. People need to go outside to explore, to conduct science, to repair the inevitable damage from this harsh world. This brings us to the next nightmare, the spacesuit. The suits we use for spacewalks today are marvels of engineering, but they are designed for the vacuum of space, where the main challenge is containing pressure and protecting against radiation. Thermal control is managed through a complex system of liquid cooling and heating, but the ambient temperature in space, while cold, is not the same as an atmosphere at minus 179 degrees. A Titan surface suit would be a different beast altogether. It would essentially need to be a personal mobile habitat, with its own insane level of insulation and heating. The visor alone would be a critical point of failure. It would need to prevent internal moisture from fogging and freezing on the inside, while not allowing the external cold to conduct inward and freeze the colonist's face. The joints at the knees, elbows and fingers would be areas of extreme vulnerability, requiring materials that remain flexible and sealed under constant cryogenic stress. The gloves are perhaps the most terrifying component. Performing delicate work, handling tools, or manipulating scientific instruments with thick, insulated gloves is hard enough in zero gravity. Doing it in cold so severe that bare skin would get frostbite almost instantly, where metal tools would stick to the gloves via cold welding, adds a layer of almost unimaginable difficulty. Every extravehicular activity would be a calculated risk, a race against the clock not just of oxygen supply, but of battery life for heating units. A suit heater failure would lead to a rapid and gruesome death, as the cold invaded the suit's layers. Now, consider what happens when something goes wrong with the habitat itself. A micrometeorite strike, a stress fracture from the settling ground, or a failure in an external system like a communications array or a heat exchanger. On Earth, or even on the Moon, a repair might be a straightforward if complex procedure. On Titan, it becomes a multi-stage logistical crisis. First, a team must suit up in those incredibly complex suits, going through airlock procedures that themselves would be lengthy to prevent massive heat loss. They would then venture out into a dim, cold landscape, their suit lights piercing the orange haze. The tool they bring must work perfectly in the cold. If it doesn't, they have to go back. The part they need to replace must be compatible. If they need to weld or solder something, traditional methods fail. The cold would suck the heat away from a weld point almost instantly, creating a weak joint. They might have to use specialized cryogenic adhesives or mechanical fastening methods. All the while, they are battling the psychological weight of the environment, knowing that a small tear in their suit, a failed seal, means instant flash freezing. The concept of instant is key here. There is no gradual onset of hypothermia. Exposing human tissue to that atmosphere would cause the fluids in and between cells to freeze solid in seconds, causing catastrophic physical damage. This ever-present danger means that all external structures and systems would need to be designed for maximum reliability and minimal maintenance. The philosophy would be build it to last forever, or at least until we can build a robot to fix it. But even robots struggle here. Their electronics generate heat which must be carefully managed to prevent overheating internally while the outside tries to freeze them. Their actuators and motors face the same lubricant and brittleness issues, so you end up in a paradoxical situation where the only way to maintain the machines that reduce human risk is to send humans out at great risk to maintain them. This extreme cold also fundamentally alters the very physics of everyday actions. For example, sound would behave differently, travelling farther and faster in the dense, cold atmosphere. A crack or a snap, like the sound of a structure straining, might be eerily clear from a long distance. Fires, as we know them, are impossible without a source of oxygen, but chemical reactions slow to a crawl. Spilling a hot drink inside a habitat would be a major event, as the steam would condense and freeze on every surface, potentially shorting out electronics. Water, the essence of life, is your enemy outside. Any moisture from breath, sweat, or a leak would instantly become ice, potentially jamming mechanisms or creating slippery hazards. The cold even affects the ground they would build on. Titan's surface is largely water ice and organic sands. Water ice at those temperatures is not slippery. It is as hard and abrasive as silicate rock. This is good for foundation stability, but it also means any excavation or construction is essentially mining through rock. The ground temperature also means that any heat leaking from a habitat would not just warm the immediate area, it could potentially melt the ice it sits on, leading to subsidence and structural collapse over time. Heat management must include not just keeping it in, but actively channeling waste heat away from critical foundation areas, perhaps through massive radiator fins exposed to the atmosphere, which themselves would be vulnerable to clogging by falling organic snow. In essence, colonizing Titan is not about adapting to the cold, it is about creating a completely separate, self-sustaining thermal oasis that is perpetually at war with its surroundings. Every watt of heat is precious, every material choice is a bet against failure, every step outside is a venture into a realm that does not just discourage human life, but actively and violently rejects it. Extreme cold is the first and most fundamental dictator of terms. It dictates architecture, energy policy, material science, operational protocols, and daily human routine. Before we can even think about farming or psychology or economics, we must answer this one question. How do we build a pocket of summer that can survive an endless winter that makes our coldest earthly nightmares look mild? Solving this is the non-negotiable ticket to even beginning the conversation about a future on that distant frozen shore. The entire endeavour hangs on our ability to master this single, brutal fact of physics. It is a challenge that pushes our engineering to the absolute limit, demanding innovations we've only begun to dream of. Success would mean creating a technology so robust it could thrive where nature intended nothing but frozen stillness. Failure is not an option, because on Titan, failure is a permanent icy silence. So you have built a fortress against the cold, a haven of warmth in that endless freeze. But the moment you contemplate a window, or an airlock, or even just the structural integrity of your walls, you face the next great adversary, the sky itself. Titan does not have a thin, vacuum-like atmosphere like Mars or the Moon. It is shrouded in a profound and heavy blanket of gas, an atmosphere that is about 50% denser than the Earth's at the surface. Stepping outside there would not feel like stepping into a void. It would feel like wading through a thick, soupy fluid. This density comes with a mix of profound challenges and one single, curious advantage. Let's start with what that air is made of, because you definitely cannot breathe it. The bulk of it, about 95%, is nitrogen, which is familiar and inert. But the remaining few percent is where things get complicated and dangerous. It is mostly methane with a touch of other hydrocarbons like ethane. This alone makes the atmosphere toxic and useless for human respiration, but it is the other component that really defines the visual and chemical experience, the haze. High in the sky, solar radiation breaks apart the methane and nitrogen molecules, allowing them to reform into incredibly complex organic compounds called tholins. These tholins create a permanent global orange smog that obscures the surface from view in orbit and turns the sky into a dim, perpetual twilight from the ground. This haze is not just a visual filter, it is a physical and chemical substance that settles out, like slow snow, coating the entire landscape in a layer of sticky, organic gunk. Now, that atmospheric density creates a surface pressure about 1.5 times that of Earth. For comparison, it is similar to the pressure you would feel swimming about 5 meters deep in a pool on Earth. This is a critical point. On Mars, the atmospheric pressure is so low that habitats have to be built like high-pressure vessels, holding in a full Earth atmosphere of pressure against a near vacuum outside. The difference is massive, and any breach would mean explosive decompression. On Titan, the pressure differential is much smaller. Your habitat only needs to hold in a slightly higher pressure than the outside. A small leak would result in a slower, more manageable hiss of air escaping, not a catastrophic explosion. From a pure engineering standpoint of habitat design, this is Titan's one major gift. Building structures to contain pressure is easier. However, that is where the advantages end, because the composition of that outside pressure turns every other aspect into a nightmare. First, there is the issue of energy, which we touched on with the cold. That thick orange haze blocks the already feeble sunlight. From the surface, the sun would appear as a faint, diffuse, bright patch in the haze, never a clear disk. This makes direct solar power almost useless. You cannot rely on solar panels on the surface. The energy budget simply does not work. You're forced into nuclear options. Second, the atmosphere is chemically active and corrosive. Those tholin particles and the constant drizzle of methane are not benign. They would gunk up mechanical systems. Imagine the optics on a camera lens or a LiDAR system constantly being coated in an oily organic film. Solar panels, if you tried to use them, would be rendered ineffective not just by the lack of light but by this constant deposition. Moving parts on any exterior machine would get this grime in their joints, potentially abrading surfaces and causing premature failure. The seals around airlock doors would be constantly exposed to it, requiring rigorous and frequent cleaning protocols to ensure they do not degrade and lose their integrity. Then there is the most acute danger: fire and explosion. The Earth's atmosphere is about 21% oxygen, which supports combustion. Titan's atmosphere has zero free oxygen. That might sound safe: no oxygen, no fire, right? The terrifying paradox is that this makes the exterior environment horrifyingly flammable. Your habitat interior will be filled with a breathable Earth-like mix, mainly nitrogen, but with a vital oxygen component. That oxygen is a potent oxidizer. If it leaks from your habitat into the Titanian atmosphere, it creates a potentially explosive mixture. Methane is fuel, oxygen is the oxidizer. Combine them, and you have the basic recipe for rocket fuel. A spark from an electrical short circuit on an exterior panel, a static discharge from a colonist's suit after traversing the organic sands, or a deliberate ignition source like a welding tool could ignite a leak, causing a fire, or even a concussive blast right outside your habitat wall. This means every external electrical system must be impeccably sealed and possibly purged with inert gases. All exterior operations require rigorous monitoring for oxygen leaks. An airlock would not just be a door, it would be a complex double or triple chamber system designed to meticulously scrub any Titanian atmosphere that clings to a returning rover or spacesuit before that inner door is opened, to prevent bringing methane inside where it could mix with internal oxygen. Conversely, it must prevent oxygen-rich air from escaping when the outer door opens. The entire colony becomes a bubble of breathable air surrounded by an ocean of fuel. Now, let's talk about what it actually feels like to be outside in that atmosphere. The high density means that sound behaves very differently. It would travel farther and with less attenuation than on Earth. A voice, or the snap of a braking tool, would carry an eerie clarity across the landscape. The winds on Titan are generally slow due to the low solar heating, but they can occasionally pick up. And because the atmosphere is so dense, even a light wind exerts a significant force. A breeze that on Earth would barely rustle leaves could push against a spacesuited colonist or a rover with noticeable pressure. A strong wind event, while rare, could be a serious hazard, potentially knocking over equipment or driving the sticky Tholin snow into every crevice. The low gravity, about 1/7 of Earth's, combined with the high atmospheric density, has another odd effect. Flight would be remarkably easy. For humans, this is not immediately useful without wings, but for vehicles, opens a possibility. Aerial drones or even winged aircraft could fly on Titan with much less power and speed than they would need on Earth. The combination of low gravity and thick air means lift is easier to generate. This could be a boon for exploration, allowing probes to cover vast distances from the air, mapping the terrain of methane rivers and hydrocarbon lakes far more efficiently than a slow, ground-based rover struggling through organic sand dunes. But again, the corrosive gunk in the air would be a constant maintenance headache for any such aircraft's engines and sensors. The atmosphere also dictates the weather and the very cycles of the landscape. Titan has an active hydrological cycle, but it is based on methane, not water. The methane in the atmosphere condenses into clouds, and it rains. This is not water rain, it is a slow gravitational drizzle of liquid methane droplets. Given the cold, these droplets are closer to a chilled liquid than anything else. They would fall onto the landscape, collecting into streams and rivers that carve channels through the water ice bedrock, eventually pooling into vast lakes and seas into the polar regions. For a colonist, this means the terrain is dynamic. You might build a habitat in what seemed like a dry valley, only to have a decade-long seasonal shift bring methane rainstorms that gradually fill the valley with a flowing hydrocarbon river. Your foundation, designed for ice and sand, now has to deal with a flowing liquid solvent at minus 179 degrees Celsius. The atmospheric chemistry also means that over long time scales, the very materials of your habitat could interact with the environment. We do not fully know how various metals, composites, or even processed ice would react to constant exposure to liquid methane and ethane. Would they become brittle in a new way? Would they slowly dissolve? The atmosphere, therefore, is not a static backdrop. It is an active chemical engine that drives the geology and the long-term environmental conditions. It necessitates a design philosophy of absolute containment and defensive engineering. Every system is about keeping the inside in and the outside out, with an airlock as the most critical and dangerous junction point in the entire colony. The psychological impact is also worth considering. The sky is not blue, it is a dome of perpetual dim orange. You would never see the stars during the Titan Day, which lasts 16 Earth days. Saturn would be a huge fuzzy presence in the haze, occasionally visible as a faint large patch. The light levels are similar to a very deep Earth twilight, just after sunset. This permanent gloom, combined with the knowledge that the very air is a toxic, flammable soup, would contribute to a profound sense of being trapped inside, of living in a terrarium under a hostile sky. The atmosphere defines the horizon, the weather, the energy constraints and the safety protocols. It turns every external mission into a hazardous materials operation. It means your life support systems are not just about producing oxygen and scrubbing carbon dioxide. They're about meticulously balancing gas mixtures to prevent any chance of combustion, and about filtering out any trace of Titan's organic compounds that might sneak in. In essence, if the cold is the immutable, physical law you must obey, the atmosphere is the active, chemical opponent you must constantly guard against. It offers one hand the gift of manageable pressure, while the other hand holds a lit match next to a fuel leak. Mastering this environment means building a civilization that is not just insulated, but hermetically sealed in a world where the sky itself is both a cushion and a threat. That thick, organic sky doesn't just sit there. It actively conspires with the cold to create perhaps the most eerily familiar yet utterly alien landscape in the solar system. A world with rain, rivers, lakes and seas, but made of substances that would be cleaning solvents or natural gas on Earth. This is the methane cycle, and for colonists it represents a dynamic, beautiful and deeply treacherous environment they must learn to navigate. Forget water. On Titan, the liquid that shapes the world is primarily methane, with a mix of ethane and other hydrocarbons. The process starts with that hazy atmosphere. Solar radiation and chemical reactions high up create complex organic molecules, but lower down, where it's cold enough, methane condenses into clouds. These aren't fluffy white water vapour clouds. They're likely dense, diffuse banks of hydrocarbon droplets suspended in the orange gloom. And when conditions are right, it rains. The rain on Titan isn't a torrential downpour like a tropical storm on Earth. Given the low energy available, it's probably more of a persistent, slow drizzle. Imagine a gloomy, drizzly day that lasts for years, with droplets of liquid methane falling through the thick air. These droplets, larger and falling slower than water droplets on Earth due to the low gravity and high atmospheric density, would eventually reach the ground. This is where the familiar becomes strange. That liquid methane, at minus 179 degrees Celsius, behaves like a very cold, runny liquid. It flows, it gathers into trickles, then streams, then rivers. Over millions of years, these methane rivers have carved intricate networks of channels and canyons into Titan's water ice bedrock, which is as hard as rock at those temperatures. The result is a landscape that, from orbit, looks startlingly like Earth. Branching river systems leading to deltas and large, dark basins. Those basins are the seas. The largest, Krakenmeer, is bigger than Earth's Caspian Sea. Others, like Ligeia Mare and Punga Mare, dot the moon's north polar region, so a colonist might, after all the struggle against cold and toxic air, stand on a rugged icy cliff looking out over a vast calm sea under a hazy orange sky. The view would be hauntingly beautiful and profoundly isolating. But you cannot drink this sea, and you cannot sail on it with a normal boat without facing a cascade of bizarre problems. First, the liquid itself is a powerful organic solvent. We don't fully know how long-term exposure to liquid methane and ethane would affect the materials we'd use for boats, submersibles, or even the foundations of a coastal habitat. Would it cause certain plastics or composites to weaken, swell, or dissolve? Testing materials in a simulation chamber on Earth is one thing. Trusting them in a vast alien sea is another. Second, the properties of this fluid are different. Its density is lower than that of water. Liquid methane is only about half as dense as liquid water. This has huge implications for flotation and navigation. A ship designed for Earth's oceans would sit much lower in Titan seas. You'd need a hull with much greater volume to displace enough of this lighter fluid to achieve buoyancy. On the flip side, the low gravity means that waves, if they occur, would be taller and move in slow motion. A 1 metre high wave on Titan would contain less energy than a 1 metre wave on Earth, but its slow, looming motion would be unnerving. The seas are also not pure methane. Radar data suggests they are mostly methane near the shores, but become increasingly ethane-rich toward the centres and depths. Ethane is even denser. This creates a layered, stratified sea where different compositions might not mix easily. There's also evidence of dissolved nitrogen, which could fizz out suddenly if the liquid is agitated or warmed, like opening a giant cold soda bottle. Now, imagine needing to explore these seas. A submarine for Titan would be a unique vehicle. It wouldn't need to withstand the crushing pressures of Earth's deep oceans, because Titan's seas, while deep, have lower gravity and a lighter fluid. The pressure at the bottom of Kraken Mare might be comparable to that a few hundred metres down in an Earth ocean, which is manageable. The thermal challenge, however, is inverted. On Earth, a submarine's hull fights to keep the cold ocean out and the warmth in. On Titan, the sea is actually slightly warmer than the icy land surface. The liquid methane might be at minus 179 degrees, but the land could be a degree or two colder. So, the submarine hull would be trying to keep a slightly warmer liquid solvent out. Any heat leak from the interior could cause localized boiling of the methane at the hull, creating bubbles of gas that might interfere with sensors or buoyancy control. The windows or viewports would need to be made of a material perfectly transparent to the wavelengths of light you want to use, but completely inert to hydrocarbon solvents. Inside, the crew would rely on synthetic lights, illuminating a dark, likely very clear liquid. What would they see? The seabed is probably a mix of water ice and accumulated organic gunk that has settled out of the atmosphere over eons. There might be methane ice or strange tar-like substances. Life? Almost certainly not as we know it, but the chemistry would be fascinating. Rivers present another set of challenges. They are the arteries of this alien hydrology, and they likely experience seasonal change. Titan has an axial tilt and orbits Saturn over a long period, creating seasons that each last about 7 Earth years. During the long polar winter, the rivers might freeze solid with methane ice. In the transition to spring and summer, they would thaw and flow, potentially causing flooding in low-lying areas. A colony built in what seemed like a dry riverbed could be inundated by a slow, cold flood of liquid methane a decade after landing. This means geological surveys to understand the hydrological history of any site would be absolutely critical, akin to building on a floodplain but with an alien solvent. The liquid also interacts with the ground, which is water ice. Methane does not dissolve water ice, but it might interact with the thin layer of organic tholins coating everything. It could facilitate chemical reactions we don't yet understand. For a colonist in a protective suit, crossing a river would be a major undertaking. You couldn't just wade through it. The liquid would rush into the seams of your suit not as a pressurized force like water, but as an incredibly cold solvent that could compromise materials and thermal integrity instantly. You'd need bridges or enclosed sealed tunnels. Collecting samples of this liquid would require specialized equipment that could prevent immediate evaporation when brought into a warmer habitat airlock. You'd need to keep it cold and under pressure to study it in its liquid state. Then there's the potential resource angle. This liquid methane is essentially a fossil fuel just sitting on the surface. The idea of using it as a fuel source is tempting but comes with a massive catch. Combustion requires an oxidizer. Titan's atmosphere has no free oxygen. So, to burn Titan's methane for energy, you would have to import or manufacture oxygen, which is an incredibly energy-intensive process, likely by splitting water ice. You might end up using more energy to make the oxygen than you'd get from burning the methane. It could make more sense to use the methane as a raw chemical feedstock, cracking it into hydrogen and carbon for manufacturing plastics or other materials, using nuclear power as the primary energy driver. The lakes and seas also present a weather phenomenon unique to Titan, probably very still, mirror-smooth surfaces most of the time, due to the low winds. This could create stunning reflections of the hazy sky, a double orange gloom above and below. But it also means that any disturbance, a landing probe, a submarine surfacing, would create ripples that might take an unusually long time to settle. The sheer scale of the hydrological activity means the landscape is not static. It is being reshaped, albeit slowly, by these alien fluids. Dunes of organic sand exist alongside river channels, suggesting a complex interplay between wind and liquid. For a colony, this dynamic environment means that long-term infrastructure planning must account for geological change. A landing pad built too close to a seashore might find itself on an eroding coastline over a century. A pipeline meant to pump liquid methane from a lake could be cut off by a shifting river channel. Understanding Titan's hydrology isn't just about science, it's about practical survival and stability. It transforms Titan from a merely hostile frozen rock into a world with active, flowing processes. That complexity is what makes it fascinating for exploration, but exponentially harder for permanent settlement. You're not just building on a dead rock, you're building on a world with its own slow, cold, liquid heartbeat, a rhythm driven by methane and the faint distant sun. Every decision about location, construction and exploration must answer to this fundamental truth. You're living on the shores of an alien ocean, where the very concept of a shore and ocean is a hauntingly familiar echo of home, built from entirely different and dangerous materials. The sound of rain here would be the soft patter of liquefied natural gas against your habitat's roof, a constant reminder that outside your warm, sealed bubble the rules of Earth no longer apply. The sound of that methane rain is a reminder of a deeper, more constant silence, the profound lack of usable energy. This is the next colossal wall any Titan colony hits. You have sealed yourself in against the cold, you have locked out the toxic, flammable atmosphere, and you look out at a landscape shaped by alien fluids. But to keep that bubble of life running, to power the heaters, the lights, the air recyclers, the computers, the scientific instruments, and eventually any industry, you need a massive, relentless and utterly reliable source of power. And Titan is, for all practical purposes, a world of perpetual darkness from an energy perspective. Let's break down why every option we have is fraught with immense difficulty, starting with the most obvious one, the sun. Sunlight at Saturn's distance is already about 100 times weaker than it is at Earth. Then, that already feeble light must pass through Titan's thick orange haze. By the time it reaches the surface, it is reduced to a dim twilight, a diffuse glow with the intensity of a very overcast day on Earth just after sunset. For solar panels, this is a death sentence. They operate on the flux of photons, and here the flux is just too low. You could cover square kilometres with the most efficient solar panels ever built, and they would still generate only a trivial trickle of electricity, completely insufficient to power even a small outpost, let alone a colony with energy-hungry heaters fighting that 200-degree temperature difference. Solar power on the Titan surface is, for all intents and purposes, useless. We must look elsewhere. The next thought might be geothermal energy. On Earth, we tap into the planet's internal heat. Titan, however, is a fundamentally colder world. Its interior is likely a mix of rock and ice, and while there is evidence from Cassini data of some internal activity, maybe even a subsurface ocean, it is not a volcanically active world like Io or even Earth. The heat flow from the interior is almost certainly minuscule. Drilling down through tens of kilometres of ice hard as rock to tap a potential lukewarm water ocean would be a monumental engineering task, akin to building an offshore oil rig in the deepest ocean. But on an alien moon where every piece of equipment is battling extreme cold, the return on investment, the amount of thermal energy you might extract, is highly speculative and likely too low to be a primary baseload power source. It might be a curiosity for science, but not a foundation for a colony, so we are left with one clear, dominant and daunting option: nuclear power. There are two main flavours to consider. The first is the radioisotope thermoelectric generator, or RTG. This is what we use for deep space probes like Cassini and the Curiosity rover. It uses the natural decay of a radioactive material like plutonium-238 to generate heat and convert that heat directly into electricity via solid-state thermocouples. An RTG is wonderfully simple, has no moving parts and can run for decades. For a small robotic outpost on Titan, a large RTG or a cluster of them might suffice. But for a full colony with humans, the power output is far too small. RTGs provide watts or hundreds of watts. A colony would need kilowatts or megawatts. That pushes us to the second option, full-scale nuclear fission reactors. These are the kind we use in submarines, aircraft carriers and power plants on Earth. They can generate the massive steady power required. But here, the challenges explode in complexity. First, there is the sheer mass and complexity of a fission reactor. You cannot build one from scratch on Titan with local materials, at least not for centuries. It must be shipped from Earth. This means designing a reactor system robust enough to survive the years-long journey, the entry through Titan's atmosphere, and a soft landing. It must then be assembled either by robots or suited colonists, in an environment where every bolt turned is a struggle against the cold. The reactor must also be designed for unattended or minimally attended operation for long periods, with incredible safety redundancies. A meltdown on Titan would be a localized catastrophe, contaminating the immediate area, but the greater risk might be the loss of the power source itself, which would doom the colony to freezing. The reactor's cooling system is another nightmare. On Earth, reactors use water, rivers, or massive cooling towers to dump waste heat into the environment. On Titan, the environment is far colder, but that doesn't simply make it easier. You need to reject the reactor's waste heat asterisk outside asterisk the habitat. But you cannot just have hot radiator fins sticking out into the minus 179 degree air. The temperature difference is so extreme that the metals could experience thermal shock. Furthermore, any heat emitted might melt the icy ground the reactor sits on, causing subsidence. And that waste heat is valuable. A smart colony would attempt to capture as much of it as possible for local heating of habitat modules, but you still eventually need to radiate the excess away into space. This requires carefully designed, likely massive radiator panels, which are another thing that can break, get coated in Tholin snow, or fail. Then there is the fuel. You need enriched uranium. That means regular shipments from Earth, or the development of a full nuclear fuel cycle on Titan, which is so far into the future it's almost fantasy. The security and safety protocols around handling and storing nuclear fuel in a small, isolated colony add another layer of operational burden. Now, let's talk about the tantalizing alternative that always comes up: burning the local fuel. Titan's lakes are literally made of methane, which is natural gas. It seems perfect, but combustion requires an oxidizer. Titan's atmosphere has no free oxygen, so to burn Titan's methane you must provide the oxygen. Where do you get oxygen? You could in theory electrolyse water, but Titan's water is locked in ice as hard as granite. To get liquid water you need to mine the ice and melt it, which takes a huge amount of energy. Then you need to use electricity to split that water into hydrogen and oxygen. The hydrogen might be used for other things, and the oxygen for burning methane. This is a process called in situ resource utilisation, but it's a net energy loser. You're using your primary energy source, likely a nuclear reactor, to create an oxidizer to burn a secondary fuel. The efficiency of this chain is terrible. You would get more usable energy by just using the electricity from the reactor directly. The only reason to do this might be to create a high-density chemical fuel for vehicles or rockets, where the energy density of methane and oxygen is worth the processing cost. But for stationary base power, it's a non-starter. You could also look at other chemical schemes, like fuel cells that combine hydrogen from water with atmospheric methane in some novel catalysed reaction, but these are speculative and unproven at the required scale. The brutal truth is that for the foundational baseload power of a colony, nuclear fission is the only game in town. This reality shapes everything. It means the colony's existence is tethered to a single, complex, high-maintenance machine. It means that the supply chain from Earth, though infrequent, must deliver nuclear components or fuel rods. It means your colony's engineers are, first and foremost, nuclear technicians. It also presents a bizarre opportunity. With abundant nuclear power, you can do things that are too energy intensive on Earth. You could run powerful arc lights to simulate a day-night cycle for agriculture, or operate massive indoor farms. You could electrolyse water on a large scale, not just for oxygen, but for hydrogen as a reducing agent in chemical industries. You could even power large-scale processing plants to crack methane into hydrogen and carbon for manufacturing of plastics or carbon fibre structures. The nuclear reactor becomes the beating heart of the colony, and its throbbing output of electricity and waste heat becomes the resource around which all other activities are scheduled. But this heart is a transplant, and a fragile one. Its failure is not an option. Therefore, you would likely have multiple reactors for redundancy, perhaps a main one and a smaller backup, both isolated in a heavily shielded power plant some distance from the main habitat, connected by heavily insulated power lines. The operation of this plant becomes the colony's central ritual. The sound of its turbines, if it uses a steam or gas cycle, or the hum of its Stirling engines, would be the constant background noise of human life on Titan, a mechanical substitute for a heartbeat, in a world where the natural one is silent and frozen. Every other challenge, food production, water extraction, material manufacturing, funnels back to this one question. Do we have the power for it? The energy budget is the ultimate dictator. It decides how warm you can keep the greenhouse, how much water you can melt, how many new modules you can fabricate. In a place where nothing comes for free, where even the air outside is useless for breathing or burning, the nuclear reactor is your tiny artificial sun, and you must worship it with maintenance and spare parts, because when it goes dark, everything else follows into the cold and the quiet. That artificial sun you have built, that nuclear heart beating in the cold, underscores the most profound and unchangeable truth of life on Titan. You're utterly, devastatingly alone. The distance is not just a number, it is a physical law that governs every aspect of existence, from your conversation with home to your very survival in a crisis. On average, Titan is about 1.4 billion kilometres from Earth. That is so far that light itself, the fastest thing in the universe, takes over an hour just to make a one-way trip. A radio signal travelling at the speed of light will take between 67 and 93 minutes to cross the void, depending on the ever-changing orbital positions of Earth and Saturn. This creates a communication delay, a light time lag, of at minimum 2 hours for a simple round-trip message. You ask a question, you wait over 2 hours for the reply. This fundamental fact dismantles the very concept of remote control or real-time assistance from Earth. Imagine a critical system failure, an alarm blaring in the control room. The colonists on site have minutes, maybe hours, to diagnose and fix it. By the time they send a panicked message to Mission Control detailing the problem, and by the time the best experts on Earth receive it, discuss it, formulate a response and send it back, 4 or 5 hours have passed. The crisis would be long over, resolved or catastrophic, before Earth's advice even arrived. This means that from the moment the first human sets foot on Titan, the colony must be completely autonomous in all critical functions. The people there are not astronauts following a detailed playbook from Houston. They are the pioneers of a new branch of humanity, and they must be the engineers, the doctors, the surgeons, the crisis managers, and the leaders. There is no calling for help. There is no quick supply drop. Every procedure from a complex habitat repair to an emergency appendectomy must be performable by the crew with the tools and knowledge on hand. This necessitates a crew with an incredibly broad and deep skill set, far beyond the specialization we see in today's space missions. They must be generalists of the highest order, trained for scenarios no one can fully predict. The delay also affects daily operations in subtler, grinding ways. Scientific exploration becomes a staggered, slow-motion conversation. A rover finds an interesting formation. The team on Titan spends a day analysing initial images, then sends a request to Earth for deeper analysis by a specific specialist. A day later, Earth gets the request. A day after that, they send back a suggested instrument package to deploy. By the time the Titan crew gets the go-ahead, 3 days have passed. The pace of discovery is governed by this lethargic ping-pong game across the solar system. For the colonists, this creates a strange psychological duality. They are constantly connected to humanity's collective knowledge via data packets, but they are living in a different time zone, one separated by a gulf of hours. A news broadcast from Earth is history by the time they see it, A personal video from a loved one is a recorded ghost from the past. This disconnect can lead to a feeling of profound isolation, a sense that the living, breathing Earth is a distant memory, a story told in delayed signals. The relationship with Mission Control transforms. They are not commanders, they are long-distance consultants, a helpful but slow library of expertise. The real-time decision-making authority shifts entirely to the colony's leadership. This autonomy is both a burden and a liberation, forcing a maturity and self-reliance unprecedented in human exploration. But the distance is not just about communication, it is about logistics. Travel to Titan is not something you do on a whim. The alignment of Earth and Saturn for an efficient Hohmann transfer orbit, the kind that uses the least fuel, occurs only once every 20 years or so. This means launch windows are rare, monumental events planned decades in advance. A colony cannot expect regular supply ships every 6 months like a space station in low Earth orbit. A resupply mission is a generational project. If you forget a critical spare part or if a key piece of equipment fails unexpectedly, you cannot order a replacement. You must manufacture it locally, cannibalize other systems, or wait possibly decades for the next cargo vessel. This places an unimaginable premium on reliability, redundancy, and in-situ manufacturing. Everything sent from Earth on that first, gargantuanly expensive mission must be designed to last for years or to be the seed for local production. The concept of just-in-time inventory is a joke. Your inventory must be for the rest of our lives, maybe our children's lives. This logistics nightmare extends to the human element. Crew rotation is not a simple matter. The colonist who goes to Titan must be prepared for a commitment measured in years, possibly decades. They're not coming home for a quick visit. The psychological selection process becomes as much about accepting permanent exile as about skills and mental fortitude. The colony must be designed from the outset to be a permanent home, not a temporary base, because temporary could mean a lifetime. This isolation also means that in a true colony-threatening catastrophe, a cascading failure of life support, a major radiation event from the reactor, a large-scale structural collapse, there is zero possibility of rescue. Earth would watch, helpless, as the messages told a story of disaster that had already unfolded hours ago. The colonists would know this. This knowledge would hang in the air, unspoken but understood, adding a layer of gravity to every risk assessment and safety protocol. It fosters a culture of extreme caution and mutual dependence, where every individual's mistake can doom the entire community, with no hope of external intervention. Yet, this very isolation could become the catalyst for a new form of society. Cut off from the incessant real-time chatter of Earth, forced to solve their own problems and govern their own affairs, the Titan colony would inevitably begin to evolve its own unique culture, norms, and identity. Their frame of reference would become the icy landscape outside, the rhythm of their own artificial day, the shared struggle for survival. Earth would slowly become an abstract concept, a place of origin and legend, but not home in the immediate sense. This cultural drift, accelerated by the communication delay, could within a few generations create a society that thinks and operates in ways fundamentally different from earthbound humanity. They would be in every sense a separate branch of our civilization. The distance thus creates a paradox. It is the primary obstacle, the source of the greatest risk and psychological hardship. But it is also the forge that would create true self-sufficiency. It forces the development of technologies and social structures that do not rely on a safety net from home. The Titan colony, to survive, must become its own planet, mentally and technologically. It must learn to mine, manufacture, farm, and heal entirely within its own closed, icy world. The dream of becoming an interplanetary species dies the moment you realize you are still tethered to Earth for every need. Titan's distance, cruel as it is, severs that tether by physics alone. To live there is to accept that severance, to look back at the pale blue dot not as a lifeline, but as a receding star in the sky, a memory, while you turn your face toward the construction of a new and utterly independent human future in the orange gloom. The silence of that long delay is not just an empty space between messages. It is the sound of childhood ending, the sound of a species learning to stand alone in the cosmic dark, with only its own wit and will to keep the lights on. Every decision, every innovation, Every success and failure on Titan would be theirs alone to own, a testament to human capability forged in the most extreme isolation imaginable. This is the final and perhaps most defining challenge, not just to survive the environment, but to survive the solitude, and in doing so, to become something new. That self-sufficiency forged in isolation finds its most critical and daily test not in machinery or engineering, but in something profoundly basic: dinner. You cannot ship food for a lifetime. You cannot even rely on occasional care packages from Earth. To survive for years, and certainly for generations, a Titan colony must master the art of growing food in a world where nothing naturally grows, under a sky that offers no nourishing light. Agriculture on Titan is not a matter of tilling soil and planting seeds. It is a high-stakes, energy-intensive feat of closed-system bioengineering. Let's be clear about the starting point. The Titan's surface is utterly barren for Earth-like life. The soil is not soil. It is a mix of water ice as hard as granite and granular organic compounds called tholins that rain down from the haze. These tholins are fascinating prebiotic chemicals, but for plants they are likely toxic, a complex tar of hydrocarbons that would poison any terrestrial crop. You cannot simply scoop up some Titan dirt, put it in a pot and plant a tomato seed. It would die, and quickly. So, traditional farming is out. This forces agriculture entirely indoors into pressurized heated modules. But even there, the first and most voracious consumer of your precious nuclear power reveals itself: light. Plants need light for photosynthesis. On Earth, that light is free, delivered by the sun. On Titan, the natural light is a dim orange glow insufficient to grow a blade of grass. Every photon that drives plant growth must be artificially generated. This means vast arrays of efficient LED lights, tuned to the specific red and blue wavelengths plants use most, blazing away for the equivalent of a long Earth day. The energy cost is staggering. Lighting alone could consume a massive fraction of the colony's total power output. This creates a brutal trade-off. More food requires more light, which requires more power from the reactor, which means less power available for other critical systems like water recycling or habitat heating. Every calorie of food produced on Titan has a directly calculable energy cost in kilowatt hours, a cost thousands of times higher than on Earth. The farming modules therefore become the colony's primary power sink after basic life support. To minimize this cost, every aspect of the growing system must be optimized for efficiency. This leads directly to soilless farming techniques: hydroponics, where plant roots dangle in a nutrient-rich water solution, or aeroponics, where roots are misted with a nutrient fog. These methods use water and nutrients far more efficiently than soil, and they allow for dense vertical farming stacks, racking plants in layers to maximize food output per cubic meter of precious pressurized volume. The fields of Titan will look like highly sterile laboratory-scale installations with racks of plants under the eerie purple glow of LEDs, their roots entwined in plastic webs or suspended in channels of flowing liquid. The nutrient solutions themselves become a critical resource. They contain essential elements like nitrogen, potassium, phosphorus, calcium, and trace minerals. Initially, these would have to be imported from Earth, but for long-term sustainability, the colony would need to recycle them perfectly. This is where human waste enters the cycle. Biological waste from the colonists cannot be discarded. It is a vital resource. Through processes like composting, anaerobic digestion, or more advanced physicochemical methods, solid and liquid waste must be broken down, sterilized, and reformulated into usable plant nutrients. The loop must be nearly perfect. Losing nutrients to inefficiency means you have to replenish them from an external source. And the only external source is 1 billion kilometers away. Water is the other half of the cycle. The plants will transpire water vapor, which must be captured by the module's air conditioning and returned to the system. Irrigation runoff must be recovered and recycled. The entire agricultural module is a tightly sealed biosphere, where every molecule of water and every atom of nutrient is tracked and conserved. A failure in this recycling loop, a pump breakdown, a fungal bloom clogging pipes, a chemical imbalance in the nutrient tank could lead to crop loss within days, and crop loss means hunger. The colony's food security would depend on the mechanical and biological reliability of these systems. Diversity is also a risk. Relying on a handful of high-yield staple crops like wheat, potatoes or soy makes the colony vulnerable to disease or system-specific failure. They would need a variety of crops for nutritional completeness and psychological well-being, but growing a wider variety means managing different nutrient, light and humidity needs, adding complexity. Some luxury crops like fruits or herbs might be grown in smaller quantities purely for mental health benefits, despite their lower calorie efficiency. This brings us to the other vital function of the farm. It's not just a stomach, it's a soul. In an environment of perpetual orange twilight outside, confined to metallic corridors, the psychological value of a green growing space cannot be overstated. The agriculture module would be the colony's garden, its park, its piece of earth. The smell of moist air and growing plants, the colour green, the simple act of tending living things, these would be powerful antidotes to depression and claustrophobia. People would likely volunteer for farm duty not just for the work, but for the therapy. It becomes a dual-purpose system, life support for the body and the mind. But this oasis comes at a terrifying price. Let's envision a scenario. A fault develops in the primary reactor, forcing a shutdown for repairs. The backup reactor can only handle critical habitat life support: air, minimal heat, water recycling. The massive power draw of the farm lights cannot be sustained. The order is given, power to the farm modules is cut. The LED arrays go dark. The constant hum of circulation pumps falls silent. For the plants, this is an immediate catastrophe. Without light, photosynthesis stops. Within hours, the plants begin to wilt. The temperature in the module starts to drop toward the ambient habitat temperature, which is still warm for humans but too cold for many crops. The nutrient mist stops. Within a day or two, the crop is lost. The colony now lives on stored food, a carefully calculated buffer that might last months. The clock starts ticking. The reactor must be fixed before that buffer runs out. There is no possibility of a resupply mission. This constant sword of Damocles hanging over the farm shapes colony culture. The farmers are among the most critical personnel. Their expertise is in botany, chemistry, systems engineering, and crisis management. They are not peasants, they are the guardians of the colony's biological heartbeat. Their work is monitored with the same urgency as the reactor's temperature readings. Furthermore, the farm dictates the colony's population size. The amount of food you can produce is limited by the power you can allocate to it, and the physical space you can dedicate to farming modules. This creates a hard ceiling on the number of mouths that can be fed. Every birth must be planned within this strict carrying capacity. The colony cannot spontaneously grow. Expanding the population requires first expanding the power supply and the farm complex, a catch-22 of monumental effort. Finally, all of this assumes we can successfully grow Earth crops in Titan's weak gravity, about 1/7 of Earth's. We don't fully know the long-term effects of low gravity on plant growth, root development, and nutrient uptake. Plants use gravity for orientation, gravitropism. Strange malformed growth might occur. This is yet another variable that must be studied and adapted to, another layer of uncertainty in an already precarious equation. In the end, the Titan farm is the ultimate symbol of the colony's fragile independence. It is a loud, bright, warm and wet rebellion against the silent, dark, cold and dry world outside. It represents the tremendous cost of replacing what Earth gives us for free, a sunlit field. Every leaf of lettuce, every potato, every grain of rice is a testament to human ingenuity and a stark reminder of their vulnerability. It is the loop that must never break, the garden that must never die. For if it does, the silence that follows will be the silence of a starving community, waiting in the dark for a rescue that will never come. The battle for survival on Titan is, therefore, fought not only with reactors and spacesuits, but with carefully calibrated nutrient solutions and the relentless, energy-hungry glow of purple lights over rows of fragile, essential green. That green and growing farm, that life-giving loop, is thirsty. It needs water. And here we encounter Titan's cruelest joke, its most profound paradox. The moon is drowning in water, yet a colonist could die of thirst. Titan holds, locked away, more liquid water than all the oceans on Earth. But it is not in the rivers or the lakes, those are methane. The water is hidden, imprisoned in a form and a place that makes it agonizingly difficult to reach. This is not a simple matter of finding an oasis. It is a problem of accessing a resource that is everywhere and nowhere all at once. Let's start with what we know. Data from the Cassini mission strongly suggests that Titan possesses a massive subsurface ocean, a global layer of liquid water sandwiched between a thick, icy crust above and a rocky, silicate core below. This is not a small aquifer. It is a planet-wide sea, likely dozens of kilometers deep, making it perhaps the largest single body of liquid water in the entire solar system outside of Earth. But it is buried. Estimates vary, but the icy crust separating the surface from this ocean is probably between 50 and 100 kilometers thick. To put that in perspective, the deepest hole ever drilled on Earth, the Kola Super Deep Borehole, reached a little over 12 kilometers after decades of effort. Drilling through 50 kilometers of ice, even ice that is relatively warm and plastic closer to the ocean, on an alien world with average surface temperatures of minus 179 degrees Celsius, is a task of almost mythic difficulty. It is not a near-future prospect for a struggling colony. It is a project for a mature, industrial-scale civilization on Titan, centuries down the line. So the ocean, while a tantalizing long-term possibility, is not the answer for the initial colonists. Their immediate reality is the surface ice. Titan's bedrock is water ice. The mountains, the plains, the river valleys carved by methane are all made of solid water ice. At those temperatures, water ice is not slippery or brittle like ice on Earth. It has the mechanical strength of granite. It is bedrock. So water is literally the ground you walk on. You're standing on it, but you cannot drink a rock. To extract usable liquid water from this, you must either physically mine the ice and then melt it, or melt it in place. Both options are monstrously energy intensive. Let's take mining first. You would need heavy machinery capable of quarrying ice rock in a cryogenic environment. Think of a mining operation in Antarctica, but where the ice is harder, the cold is more extreme, and every piece of equipment is at risk of brittle fracture. You would chunk out blocks of ice, transport them to a processing facility, and then feed them into a melter. The melter is the real problem. To turn ice at minus 179 degrees into liquid water at 0 degrees requires raising its temperature by nearly 180 degrees. The specific heat capacity of ice means this demands a huge input of energy. Using your precious nuclear power, you would be diverting electricity to heating elements or microwave systems to slowly, laboriously, and expensively liquefy your mined ice. The process would be slow, and the water yield per unit of energy would be dishearteningly low. The alternative, melting in situ, presents different challenges. You could theoretically use a heated probe or a drilling system that melts its way down, creating a borehole and pumping the resulting slush or water to the surface. This is called cryo-drilling. But again, the energy cost to maintain the heat at the drill head against the relentless conductive cold of the surrounding ice is enormous. Furthermore, the water you produce, if not managed perfectly, could refreeze in your pipes instantly, causing catastrophic blockages. Any system for water extraction would be a network of heated, insulated pipelines and tanks, another major draw on the power grid. And for what? Initially for drinking, for hygiene, and to feed the hydroponic farms. But the vision goes further. Water is not just for life support, it is a chemical feedstock. Through electrolysis, you can split water into its component parts, oxygen and hydrogen. Oxygen is for breathing and for potentially burning with methane for high-thrust rocket fuel or emergency generators. Hydrogen could be a useful reducing agent in chemical industries or combined with carbon from the atmosphere to make plastics or other materials. So, accessing local water is the key to long-term chemical independence from Earth. But the barrier to entry is that staggering energy cost. This creates a vicious cycle in the early years of the colony. You need water to expand and become self-sufficient. But to get abundant water, you need a massive amount of power. To get more power, you likely need to build additional nuclear reactors, which is a huge undertaking requiring infrastructure you might not yet have. And to support that infrastructure and the people to build it, you need more water and food. It is a classic bootstrapping problem. Therefore, the early colony would be utterly dependent on perfect water recycling, just like on the International Space Station, but on a larger, more critical scale. Every drop of moisture from breath, sweat, urine and farm transpiration would be captured, purified and reused. The tolerance for loss would be zero. The water you brought with you from Earth, stored in massive insulated tanks, would be your strategic reserve, your emergency buffer, but not your primary source. You would use it to top up the inevitable minor losses in the recycling system. This makes the water recyclers among the most vital and carefully maintained machines in the entire habitat. Their failure would mean tapping into the reserve, and once that's gone, you face the desperate, energy-crushing task of trying to melt enough surface ice to survive, likely under crisis conditions. There is another layer to this challenge: the quality of the ice. Titan's surface ice is not pure. It is likely mixed with ammonia and other contaminants from the atmosphere and geological processes. Ammonia water ice has a lower melting point, which could help, but it also means your melted water would be a toxic brine requiring extensive desalination style processing to remove the ammonia and other salts before it is safe to drink or use in the farm. This adds yet another step, more equipment and more energy to the process. So, the picture that emerges is one of a resource that is globally abundant but locally locked. For the first colonists, water will feel scarce. It will be measured, rationed in terms of energy expenditure. Taking a long, hot shower would be an unspeakable luxury, a waste of energy that could have melted 10 kilograms of ice for the farm. The colony's water would probably be tepid, strictly metered and constantly monitored. The act of finally establishing a reliable, large-scale water mining and melting operation would be a milestone akin to discovering a freshwater spring for a desert settlement. It would mark the transition from a precarious outpost to a truly growing colony. It would allow for population expansion, larger farms, and the beginnings of local industry. But until that day, the colonists lived with the irony of being surrounded by the fundamental compound of life, in quantities that dwarf their home planet, yet unable to access a drop without a fierce technological fight. Their world is a watermark in a freezer, and they are the tiny source of heat trying to coax a drop out of it, knowing that the ocean beneath their feet is as distant as a dream. This reality shapes their mindset. They are not pioneers on a desert world praying for rain. They are technicians in a freezer trying to defrost a continent with a hairdryer, knowing the work of centuries lies ahead to truly quench their future's thirst. The water is there, but Titan's deep cold is the jailer, and energy is the only key, a key they must forge themselves, watt by precious watt. That rationed water, that constant calculation of energy versus survival is just one part of the daily weight. The true test, the one that grinds down over months and years, is not the machinery, but the mind. You're living in a can, a meticulously engineered can, but a can nonetheless. The psychological reality of colonization is the relentless, inescapable confinement under an alien sky. You cannot step outside for a breath of fresh air. You cannot feel sunlight on your skin. You cannot hear birds or the wind in trees. Every single experience of the natural world is mediated through layers of technology, or replaced entirely by a synthetic substitute. Your entire universe is a series of interconnected modules, corridors, and pressurized domes. The walls are always there. You will know every scratch on every surface, every hum of every ventilator, every faint smell of recycled air and ozone. This claustrophobia is not an occasional feeling, it is the permanent state of existence. The only view of the outside is through windows, and what does that window show? A perpetual dim, orange-brown twilight. The haze is so thick you cannot see stars during the day. The sun is a diffuse, weak, bright patch, never a distinct disk. The landscape is a monochrome of dull oranges, browns and greys lit by this eerie gloom. It is not a vibrant, inspiring vista. It is a stifling, oppressive blanket. Occasionally the massive bulk of Saturn might hang in the haze, a hauntingly beautiful but distant presence, a reminder of how far you are from anything familiar. This visual monotony would be psychologically draining. Humans need visual variety, changes in scenery, to stay mentally healthy. On Titan, the scenery never changes unless you actively change the screen on your personal device to show an earth forest or a beach. You are living inside a painting of gloom, and you cannot leave the frame. Then there is the time. A day on Titan, the time it takes to rotate once on its axis, is about 16 Earth days. This is catastrophically disruptive to the human circadian rhythm. Our bodies are tuned to a 24-hour cycle of light and dark. Living on a 16 Earth day cycle would throw that biological clock into complete disarray. You could not adopt the local day, it would be madness. So, the colony must enforce an artificial 24-hour schedule. Lights in the living modules brighten and dim on a strict Earth time clock. You eat breakfast, work, have dinner, and go to night based on a rhythm that has no connection to the world outside your walls. Your body might constantly feel out of sync, jet-lagged forever. This requires rigorous personal discipline and colony-wide adherence to the schedule. Sleeping aids and light therapy might become as routine as taking vitamins. The social fabric is strained by this artificiality and by the sheer unrelenting proximity. You're trapped with the same few dozen or 100 people for years. There is no walking away. A personal conflict cannot be resolved by taking a walk to cool off, because the walk is just 3 laps around the central habitat corridor. Every grievance, every personality clash, every minor annoyance is magnified by the constant, inescapable contact. The stress is compounded by the knowledge that in this small, isolated group, everyone's survival depends on everyone else's flawless performance. The person you had a stupid argument with at breakfast is the same person whose attention to detail might prevent a life support failure that evening. You must trust them with your life, even if you currently dislike them. This creates an immense pressure to suppress normal human emotions, to maintain a facade of professional harmony at all costs, which in itself is emotionally exhausting. Resentments can fester under the surface. The isolation from Earth, the communication delay intensifies this. You're disconnected from the evolving culture of your home planet. News is old. Trends pass you by. Your friends and family age in jumps, seen only in quarterly video messages that feel like watching historical archives. You might experience a profound sense of being left behind, of your old life moving on without you. This can lead to depression, a feeling of meaninglessness, or a deep nostalgia that borders on grief. The colony's purpose, scientific discovery, the survival of the species, whatever the founding ideal, must be powerful enough to counteract this existential weight. Every colonist must buy into the why with fanatical conviction, or they will break. This necessitates the most rigorous selection process ever devised. It is not about IQ or physical strength alone. It is about psychological resilience, emotional stability, teamwork under stress, and an almost monk-like acceptance of a life of extreme routine and unlimited personal freedom. Candidates would undergo years of evaluation, including long-duration isolation tests in Earth-based simulators that mimic the confinement and interpersonal dynamics of the Titan habitat. Even then, selection is a gamble. People can change over years in isolation, which is why ongoing psychological support is not a perk. It is as critical as the oxygen system. The colony would need embedded psychologists, and mental health check-ins would be as routine as physical exams. There would need to be structured outlets for stress, virtual reality environments offering escapes to Earth-like settings, intense physical exercise regimens, art and music creation spaces, and carefully managed social events. Privacy, in whatever tiny form it can take, would be a precious commodity. Personal quarters, even if just a small sleeping pod, would be vital sanctuaries. The architecture of the habitat would need to consider sightlines and acoustics to minimize the feeling of being constantly observed. Yet, the very environment fights against this. The constant background noise of machines, the ever-present artificial light, the lack of natural sensory stimulation, all of it contributes to cognitive fatigue. Your brain, evolved to process a rich stream of sensory data from a natural world, is starved. It is fed a bland, repetitive, synthetic diet. This can lead to attention deficits, irritability, and a decline in cognitive function over time. Countermeasures would need to be creative and persistent. Perhaps large, immersive video walls showing dynamic Earth scenes, or complex tactile workshops where people can work with their hands on real materials. The farm module, as mentioned, becomes a critical psychological refuge precisely because it offers a real sensory experience. The smell of soil or nutrient solution, the humidity, the colour green, the tactile experience of tending plants. It is a tiny piece of a living Earth, and its importance for mental health cannot be overstated. But the ultimate psychological challenge is the acceptance of a new normal. The colonists must, over time, stop comparing their environment to Earth. They must stop seeing the orange sky as oppressive and start seeing it as their asterisk sky. The hum of the reactor must become the sound of home. The corridors must become familiar streets. This mental shift from being an Earth person in an alien place to being a Titan person is essential for long-term sanity. It is the process of building a new cultural identity, one born of shared hardship and extraordinary purpose. For the first generation, this is a struggle. There will always be immigrants, but for their children, born under the dome, this will simply be the world. Their psychology will be Titanian, shaped by the walls and the gloom and the stories of a blue planet far away. The success of the colony, therefore, hinges not just on solving the technical puzzles of air and water, but on nurturing a society that can find meaning, joy and human connection inside the can, under the perpetual orange twilight, forever separated from the vibrant world that gave them life. It is a test of the human spirit in its most confined form, asking whether we can build a home where nature never intended one, and find a way to be happy within the limits we've drawn for ourselves against the void. That new identity, that Titanian sense of self, will be shaped not just by the mind's struggle with confinement, but by the body's quiet, relentless rebellion against a fundamental lack: weight. The gravity on Titan is not like Earth's, or even Mars's. It is a whisper of a pull, just 13.8% of what we feel at home. To put that in perspective, it is even lower than the gravity on our own moon. You would weigh about 1/7 of your Earth weight. Now, that might sound fun at first. Imagine the leaps, the ease of moving heavy equipment, the sheer novelty of it. And in the short term, for construction and movement, it offers genuine advantages. But for the human body, built and calibrated over millions of years for one full Earth gravity, this low pull is not a perk. It is a slow motion disaster. The human body is a dynamic system that constantly rebuilds itself in response to stress. Our bones and muscles are maintained by the daily work of fighting gravity. Stand up, walk, lift things. These activities send signals that tell your body to deposit calcium in bones and maintain muscle mass. Remove that constant gravitational stress, and the body, in its efficient but short-sighted way, decides these strong bones and bulky muscles are an unnecessary waste of energy. It starts to dismantle them. We have seen this on the International Space Station in microgravity. Astronauts lose bone density at a rate of about 1 to 2% per month, particularly in weight-bearing bones like the hips and spine. They lose muscle mass and strength just as rapidly, no matter how much they exercise. Their cardiovascular system also becomes deconditioned. The heart doesn't have to work as hard to pump blood, so it weakens. Fluids shift upward toward the head, causing a constant stuffy feeling and long-term changes in vision. Now imagine that, but for years, for a lifetime. Titan's gravity is not microgravity, but it is so low that the same degenerative processes would occur, just perhaps at a slightly slower rate. The body would still sense that it is not working against a full gravity load. The consequences are severe and multifaceted. First, osteoporosis in space is not like old age osteoporosis on Earth. It is rapid, systemic, and can lead to irreversible changes. A colonist on Titan could suffer from weakened bones prone to fractures from what would be a minor stumble on Earth. A simple slip in a corridor could result in a broken hip or a compression fracture of the spine. These are catastrophic injuries in a place where medical resources are limited and full rehabilitation is nearly impossible. Second, muscle atrophy affects not just limbs but the core and back muscles, leading to chronic pain and poor posture. It also affects the heart, a muscle that will shrink and weaken. Upon any return to Earth gravity, if that were even possible, this weakened heart might struggle to maintain blood pressure, leading to fainting and cardiac strain. But the third, more insidious effect is on the sensory systems. Our inner ear, which helps with balance and spatial orientation, relies on gravity. In low gravity, the signals it sends to the brain become confused and unreliable. Colonists would likely experience a kind of perpetual low-grade space adaptation syndrome, feeling off balance or queasy for months. Their coordination would be off. Their sense of up and down might become fluid, tied more to visual cues from the habitat's architecture than to their own vestibular system. This could lead to disorientation, especially in large open spaces within the habitat or during complex external operations in a spacesuit. Now, the obvious solution is exercise. On the ISS, astronauts spend 2.5 hours a day, every day, strapped to resistance machines and treadmills, just to mitigate the worst of the effects. On Titan, this would be non-negotiable, but it would be even harder. The exercise regimen would need to be more intense, more prolonged, to provide the necessary loading in such a weak gravitational field. Imagine having a second job that is nothing but daily, grueling, high-impact workouts, just to keep your skeleton from dissolving. This is time and energy diverted from other tasks, and it is mentally exhausting. Furthermore, the equipment for this, heavy resistance machines, centrifuges, vibrating plates, would be massive, complex and power-hungry to import and maintain. Another idea is artificial gravity created by rotation. This is the classic spinning space station from science fiction. You could build a large rotating habitat, a wheel or a cylinder, where centrifugal force simulates gravity. For a colony on a moon, this is incredibly difficult. You're building on a surface, not in free space. You could construct a large rotating ring within a stationary protective shell, but the engineering challenges are monumental. The bearings would have to be flawless to prevent seizing in the cold, the structure would be massive, and a failure of the rotation mechanism could cause a disaster. It is likely beyond the capability of an early colony. So, the more plausible countermeasures are personal and pharmacological. Colonists might wear weighted suits or vests during their daily activities to increase their effective body load. They might take bisphosphonate drugs to slow bone loss. They might use lower body negative pressure devices, like sealed trousers that suck blood toward the feet, to simulate the fluid pressures of Earth gravity. But all of these are partial, imperfect solutions. The grim reality is that a long-term colonist on Titan will undergo permanent physiological changes. Their bodies will adapt to that 13.8% gravity. Their bone structure will remodel to be lighter. Their muscles will find a new equilibrium at a lower strength level. Their cardiovascular system will adjust, and in doing so, they will likely lose the ability to ever return to Earth. The journey home would be physically impossible. The acceleration forces of launch, even if they could survive them in their weakened state, would be followed by the nightmare of readapting to full Earth gravity. Their hearts would fail, their bones would fracture under their own weight. They would be, in effect, prisoners of Titan's gentle pull. This has profound implications. It means colonization is a one-way trip, not just logistically, but biologically. It means the selection process must find individuals who accept not only leaving Earth behind, but leaving their very physical potential as Earth humans behind. They are volunteering for a form of controlled evolution. For children born on Titan, this is their native environment. Their bodies will develop under this low gravity from conception. Their bones may be more porous, their stature perhaps taller and more slender due to the reduced compressive load on the spine. They may never develop the robust musculature of an Earth human. They will be Titanians, physiologically distinct from their ancestors. A visit to the homeworld for them would be a lethal excursion to a high-gravity prison planet. This physical separation cements the cultural and psychological separation. It turns the colony from an outpost into a genuinely new branch of humanity, with a different relationship to the very concept of weight and movement. Daily life would reflect this. Movement would be a series of careful, controlled pushes and floats. A running step could send you sailing into a low arc. Dropping a tool doesn't mean it falls quickly to your feet. It drifts down in a slow, graceful arc, giving you time to catch it. Spills would be messier, with liquids forming wobbling globules. Every physical action requires recalibration. This constant low-level need for motor control adjustment is cognitively tiring. It adds another layer of background stress to an already stressful existence. Furthermore, we do not know the long-term effects of low gravity on systems we take for granted. Pregnancy and fetal development, the functioning of the lymphatic system, wound healing, and even the risk of certain cancers. Titan becomes a grand involuntary experiment in human biology. The medical facility would be focused not on treating Earth diseases, but on managing the pathologies of low-gravity living. Kidney stones from calcium leached from bones, spinal disc issues, balance disorders, and the psychological impact of a changing body image. In the end, the low gravity is a silent, pervasive factor in every other challenge. It makes constructing large habitats easier, but it makes keeping the builders healthy nearly impossible. It offers the freedom of near flight, but at the cost of a permanent degenerative sentence for the human form. It is the ultimate trade-off, the ease of engineering and a gentle gravity well versus the slow unravelling of the engineer. The colonists will not be superheroes in a low-gravity paradise. They will be patients in a long-term care facility for gravitational deficiency, fighting every day to slow the decay, knowing that complete victory is impossible, and that their future, and their children's future, is one of permanent adaptation to a gentle but alien pull. That adaptation to Titan's gentle pull happens within a landscape that is itself a frozen monument to chemistry, a vast laboratory where the rules for creating life's ingredients are written, but the final step, life itself, seems absent. This is the world of prebiotic chemistry, and for colonists it is both a treasure trove of potential resources and a minefield of unknown hazards. Forget the idea of a sterile, inert rock. Titan's surface is coated in the complex organic gunk that results from its atmospheric drama. High above, ultraviolet light from the sun and charged particles from Saturn's magnetosphere smash into the molecules of nitrogen and methane. This relentless energy shatters these simple compounds, allowing the fragments to recombine into ever more complex organic molecules. These molecules eventually clump together into reddish-brown particles that make up the pervasive haze, and they slowly drift down, snowing out over millions of years to coat the entire surface in a layer of material scientists call tholins. This is not a single substance, but a vast complex mixture of hydrocarbons, nitriles, and other carbon-rich compounds. It is the stuff of life's building blocks, amino acids, nucleotide bases, but frozen solid and trapped in a chemical deep freeze at minus 179 degrees Celsius. For a scientist, it is a wonderland, a frozen snapshot of the chemical steps that might have led to life on Earth billions of years ago. For an engineer trying to build a lasting colony, it is a sticky, corrosive, and unpredictable nuisance. First, consider the sheer ubiquity of this material. It is everywhere. It stains the water-ice bedrock orange and brown. It forms dunes around the equator, vast seas of granular organic sand. It settles on every surface inside every crevice. When it rains methane, it likely falls as a mud, a mixture of liquid hydrocarbons and tholin particles. This means any structure, any piece of equipment left outside will be coated. Imagine the grime on a city windowsill after a year, but this grime is a chemically active, unknown organic sludge. For moving parts on rovers, drills, or antennae, this coating is a serious threat. It could act as an abrasive, grinding at seals and bearings. It could absorb trace atmospheric moisture and become acidic, promoting corrosion on metal parts. It could gum up mechanisms, causing them to seize. The seals around airlock doors would be particularly vulnerable. A build-up of tholin grime could prevent a perfect seal, leading to a slow, dangerous leak of breathable air. Keeping external systems operational would require constant, tedious cleaning regimens, performed by suited colonists or specialised robots in that brutal cold. Then there is the direct chemical interaction. We do not have a complete library of how every Earth material reacts with this titanian organic mix over long periods. Certain plastics or composites might swell, weaken, or dissolve upon prolonged contact. Wiring insulation could become brittle. The transparent viewports on habitats or vehicle cabins could become etched and clouded. Every material choice for the exterior of anything must be tested against this specific environment, a process that is itself difficult and time-consuming given the challenge of perfectly simulating Titan's conditions on Earth. Furthermore, this organic layer complicates surface travel. The dunes are not made of silicate sand like on Earth or Mars. They are made of these tholin grains. Their physical properties, how they compact, how they slide, how they behave under a rover's wheels, are largely unknown. A vehicle could easily become stuck in a deceptive patch of loose organic powder. Now, let's flip the perspective. This annoying, pervasive gunk might also be the colony's greatest chemical resource. The colonists have brought with them a finite supply of everything from Earth. But here, literally lying on the ground, are the raw materials for manufacturing. Tholins are rich in carbon and nitrogen. With sufficient energy and clever chemistry, you could potentially process them to extract useful elements and compounds. The carbon could be used to make carbon fibres, graphene, or simple plastics for 3D printing replacement parts. The nitrogen is crucial for making fertilizers for the hydroponic farms, and it could be fixed into ammonia or other compounds. Instead of importing every kilogram of polymer or composite from Earth, a colony could aspire to create a local manufacturing base using this indigenous feedstock. This is the dream of in-situ resource utilization, pushed to its extreme. You would need industrial-scale chemical processing plants, which again circles back to the need for abundant nuclear power. You would need to develop entirely new chemical engineering processes, designed to work in extreme cold, perhaps using liquid methane as a solvent in your chemical reactors. But the potential payoff is a giant step toward true self-sufficiency. The methane lakes themselves are another part of this chemical resource. They are not just potential fuel, they are reservoirs of relatively pure hydrocarbons that can be fractionated and processed. Ethane could be separated and used as a feedstock for producing ethylene, the cornerstone of many plastics. The atmosphere itself is a source of nitrogen and methane. With enough energy, you could crack methane into hydrogen and carbon. The hydrogen could be used to hydrogenate other organics or as a component in fuel cells. However, this grand vision is tempered by a massive scientific and ethical caution. Titan is perhaps the best natural laboratory for prebiotic chemistry in our solar system. Its environment allows us to study the steps that lead from simple molecules to complex ones, steps that are hidden in Earth's distant past. A human colony with its inevitable contamination risks ruining this pristine experiment forever. We are bags of water filled with Earth-based organic molecules, and more importantly, microbes. A soup tear, a habitat leak, a discarded piece of organic waste. Any of these could introduce terrestrial biology into the Titan environment. Even if life cannot propagate in the liquid methane lakes, which is likely as our biochemistry is water-based, the introduction of Earth's organic signature could irrevocably muddy the chemical data. The tholins on the surface are inert due to the cold. Chemical reactions there proceed at a glacial pace. But what if we warm them up locally? What if our industrial processes create microenvironments where novel chemistry could occur? We might inadvertently create something, or worse, destroy the very evidence we came to study. Therefore, any colony would have to operate under planetary protection protocols far more stringent than those for Mars. This means complete sterilization of all equipment before landing and incredibly rigorous containment procedures once on the surface. The colony would be a bubble of Earth biology in a sea of prebiotic chemicals, and the barrier between them must be absolute. This adds another layer of operational complexity. Exiting the habitat isn't just about suiting up for the cold, it's about ensuring you do not bring Earth life out or bring Titan organics in. Decontamination airlocks would be standard, perhaps involving UV baths, chemical washes, or intense heat cycles for returning equipment. The scientific study of the local chemistry would have to be conducted in sealed, sterile laboratories within the habitat, with samples meticulously cleaned before entry. For the colonists, this means the fascinating landscape they look out upon is also a museum they must not touch carelessly. Their daily work is a tightrope walk between using the environment to survive and preserving it for science. This duality defines their relationship with Titan's chemistry. It is not a passive backdrop, it is an active participant. It threatens their machines, but it offers the materials for their independence. It is the subject of their most profound science, but it is also a fragile record they must not smudge with their own biological fingerprint. In their hands, a handful of Titan sand is not just dirt. It is a mystery billions of years in the making, a potential building block for their future, and a possible contaminant all at once. Mastering this world means learning its chemical language, learning to work with it without destroying its native voice, and perhaps one day using its own frozen words to write the next chapter of human settlement. The challenge is to move from being clumsy, contaminating guests in this chemical laboratory, to becoming its careful stewards and adept apprentices, learning to build with the very bricks that nature has spent eons slowly, coldly manufacturing in the orange haze above. The sticky, chemically complex tholin dust covering everything is just the first insult to any man-made object. The deeper, more fundamental problem is that the very stuff we build things from was never designed for such a place. The challenge of materials and construction on Titan is a foundational one, literally. You cannot build a home, a factory, or even a simple storage shed with terrestrial engineering. Every bolt, every weld, every seal, and every beam faces a silent, relentless enemy in the constant minus 179 degrees Celsius cold. This is not merely about staying warm inside, it is about the structural integrity of the walls themselves. Consider common terrestrial materials. Steel, the backbone of modern construction, becomes perilously brittle at cryogenic temperatures. The ductility, the ability to bend and deform slightly without breaking, vanishes. Under stress, a steel support might fracture catastrophically rather than bend. Aluminum alloys fare somewhat better, but they too lose toughness. Plastics and polymers used for insulation, wiring, seals, and gaskets undergo a transition called the glass transition, where they become hard, stiff, and fragile. A rubber O-ring sealing a critical hatch would harden like glass, losing all elasticity, and could shatter under pressure or fail to seal completely. Lubricants solidify, turning gears and bearings into locked, grinding messes. Even advanced composites like carbon fibre reinforced polymers can suffer from differential contraction. The resin matrix and the fibres contract at different rates in the cold, leading to microcracks and delamination. This means that nothing from the Home Depot catalogue works here. Every single component must be specially engineered for cryogenic service. This likely involves developing entirely new metal alloys, perhaps based on nickel or titanium, that retain ductility at extreme low temperatures. Polymers would need to be specially formulated with plasticizers and structures that resist glass transition. Seals might rely on exotic multi-layer designs or entirely different sealing principles, like cryogenic adhesives or perfectly machined metal-on-metal contacts. But even if you solve the material science puzzle for imported parts, the scale of a colony means you cannot possibly ship every beam and panel from Earth. You must learn to build with what is locally available, and on Titan the most abundant local structural material is water ice. At those temperatures, water ice has the mechanical strength of limestone or granite. It is a bedrock. The concept of icecrete or pycrete has been around in science fiction for years, mixing ice with some fibrous material to create a strong concrete-like substance. On Titan, you could theoretically quarry blocks of water ice, or use industrial processes to melt and refreeze it into desired shapes, potentially reinforcing it with shredded polymers or even local organic fibres. Building with ice seems logical. It is strong, it is everywhere, and it provides excellent radiation shielding. You could carve habitats directly into ice cliffs or 3D print large domes from melted and refrozen ice. However, the engineering realities are brutal. First, ice is not an insulator. It is a conductor of heat. An ice habitat would be thermally catastrophic without an immense internal insulation layer, because the heat from inside would readily flow into the ice walls, melting them and destabilizing the structure. So an ice structure is really just a shell. Inside it, you would still need to build a fully insulated, pressurized metal or composite habitat. The ice acts as a radiation shield and micrometeorite protection, but not as a primary pressure vessel. Second, the foundation problem is extreme. Titan's surface is not stable bedrock in the terrestrial sense. It is a complex layering of water ice, organic sediments, and possibly methane clathrates. It is subject to geological processes like cryovolcanism, where slushy mixtures of water and ammonia might erupt, and tectonic stresses from tidal forces from Saturn. The ground could shift. An ice block structure sitting on such terrain could crack or settle unevenly. Furthermore, any heat leakage from the habitat, however minor, could melt the ice it sits on, causing slow, insidious subsidence. You would need active cooling in the foundations to keep the ground frozen, which is a bizarre inversion of Earth engineering where we fight frost heave. Now, think about the actual construction process. It would need to be almost entirely robotic or performed by suited humans in an environment where tools fail. A simple nail gun is useless. Nails would shatter. Welding is a nightmare, as the intense heat would cause wild thermal gradients, and the weld pool would freeze almost instantly, creating a weak, porous joint. Adhesive bonding might be a primary method, but you need adhesives that cure properly in the cold and remain flexible. Mechanical fasteners like bolts would need to be made from compatible cryogenic-tolerant alloys and torqued with exquisite care to avoid stripping or fracturing. Every single connection point is a potential failure point. The construction site itself would be a dim, cold hellscape. Cranes and lifts would need specially formulated hydraulic fluids and lubricants. Power tools would overheat internally while their exteriors are cryogenically frozen. Batteries would lose most of their capacity. The pace of work would be glacial, pun intended. Prefabrication becomes key. The ideal scenario is to land fully assembled, self-contained habitat modules from Earth, designed as perfect sealed units. Then, robots would entomb these modules in locally quarried ice for protection, or connect them with pre-made flexible tunnels that can tolerate some ground movement. Expansion would involve landing new modules, not building from scratch with local ice. Only much later, with a fully established industrial base. Could more ambitious ice construction begin? This reliance on prefabricated Earth modules makes the colony extremely vulnerable in its early decades. A module failure is not repairable in a conventional sense. You might need to seal it off and abandon it. The colony's growth is limited by the staggering cost and rarity of launching these perfect cryo-rated capsules from Earth. There is also the constant battle against the atmospheric chemistry. As discussed, the Tholin dust and methane rain are not neutral. They could interact with construction materials over time. Ice structures could become stained and their surface chemistry altered, potentially affecting their structural properties or how they interact with sealants. Metal surfaces might experience cold welding, where two very clean cold metal surfaces in contact fuse together, making disassembly impossible. All of this means that the architecture of a Titan colony is not about grand, elegant designs. It is about robustness, redundancy, and simplicity. Shapes are likely to be rounded to distribute stress and minimize points where Tholin dust can accumulate. Surfaces are smooth to aid in cleaning. The entire structure is probably elevated on pilings with active cooling elements to prevent ground melt. The layout is modular, so a failure can be isolated. It is engineering driven purely by survival, not aesthetics. Every square metre of habitat represents a triumph over a hostile physics that wants to make every material fail, every joint leak, and every foundation sink. The colonists are not just living in a building. They are living inside a monument to material science, a tiny bubble of carefully maintained order where the normal rules of construction have been rewritten from first principles to defy a world that treats human ingenuity with absolute, frozen contempt. That monument to material science, that triumph of engineering, has a price tag so large it defies earthly comprehension. We've been talking about survival, about overcoming physics and chemistry, but all of that rests on a foundation of money, logistics, and cold, hard economic reality. The logistics and economy of a Titan colony are not just challenging, they're arguably the most insurmountable barrier of all, the filter that makes the entire endeavour a dream rather than a near-term plan. Let's start with the sheer, jaw-dropping cost of getting anything there. Titan is, on average, 1.4 billion kilometres away. Every single gram of material you want on its surface must be launched from Earth, accelerated out of our planet's gravity well, sent on a multi-year journey across the solar system, inserted into orbit around Saturn, and then landed on Titan through its thick atmosphere. We are not talking about a few metric tons for a Mars rover. A sustainable colony would require thousands of metric tons of initial hardware, habitat modules, nuclear reactors, life support systems, mining equipment, food supplies, and spare parts for decades. Even with the most optimistic projections of future heavy-lift rocket technology, like SpaceX's Starship or its successors, you would need dozens, perhaps hundreds, of dedicated launches just to assemble the interplanetary transport vehicle in Earth orbit. That vehicle itself would be a colossal spacecraft, needing propulsion for the years-long journey and landing systems for Titan. Each launch from Earth costs hundreds of millions of dollars. The multiplication is astronomical. The total price tag for just the initial setup could easily run into the trillions of dollars, a sum that dwarfs the entire historical budget of NASA. No single nation would undertake this. It would require a sustained global economic effort akin to a world war, but without the perceived immediate threat. And for what will return, this is the second and perhaps fatal economic problem. There is no clear economic justification. Colonization for science is noble, but science budgets are limited. Colonization for the survival of the species is a long-term philosophical goal, not an economic driver. On Earth, colonization historically followed trade or resource extraction. The New World had timber, furs, tobacco, gold. Titan has what? Its most abundant surface resources are water ice and hydrocarbons. Water is valuable in space, but Titan is arguably in the worst possible location to sell it. The water-rich asteroids of the inner solar system are far closer to potential customers like Mars or lunar bases. Transporting water ice from Titan to anywhere else would be absurdly expensive. The hydrocarbons, the methane and ethane in the lakes are fascinating, but they are not scarce on Earth. We have natural gas. Shipping Titanic methane 1 billion kilometres to compete with terrestrial fracking is economic nonsense. There are no precious metals lying around, no titanium mines despite the name, no rare elements we know of that would justify such an extravagant freight cost. So, the colony cannot export anything of monetary value back to Earth. It cannot pay for itself. This means it would be a permanent gargantuan money pit, funded by the taxpayers or philanthropists of Earth, forever. This is not a sustainable economic model. Any colony would exist purely on charity and the continued political will of a distant planet that receives nothing tangible in return except data and inspiration. History suggests that kind of support is fickle. When budgets tighten or political priorities shift, the distant and expensive colony becomes the first thing to cut. Without an economic engine, the Titan colony would live under a constant sword of Damocles, its lifeline subject to the whims of Earth's politics. This forces a radical rethinking of the colony's internal economy. Since it cannot trade meaningfully with Earth, it must become a closed, self-sufficient loop as quickly as possible. Its economy becomes about the internal production and exchange of goods, services and knowledge. Energy credits, based on the output of the nuclear reactor, might become a de facto currency. A farmer's work producing food is traded for an engineer's work fixing a water recycler, but this is a subsistence economy, a survival economy. It does not generate surplus wealth for growth or innovation beyond bare necessities. For the colony to advance, to build new modules, to expand its industry, it needs an influx of capital from outside, which circles back to the problem of Earth's charity. Perhaps the only export with conceivable value is intellectual property, the scientific discoveries, the engineering solutions for cryogenic living, the data on prebiotic chemistry. This knowledge could be beamed back to Earth for free. But can you build a trillion-dollar economy on patent royalties and Nobel Prizes? Unlikely. There is a speculative long-term vision where Titan's hydrocarbons become valuable as rocket fuel for further exploration of the outer solar system. Titan could become the gas station of the Saturnian system, or a hub for missions to the ice giants Uranus and Neptune. But this requires a pre-existing, robust traffic of spacecraft in the outer solar system which does not exist. You're building a gas station in a desert where no cars are driving, hoping the cars will come later. The colony would have to exist for decades, perhaps centuries, before this potential economy could materialize. The logistical nightmare also dictates an excruciatingly slow pace of development. With launch windows opening only every 20 years, the colony's growth happens in slow, punctuated leaps. A wave of new colonists and equipment arrives, then 2 decades of work integrating them and building with what you have, then another wave. There is no rapid iteration. A mistake in planning cannot be corrected with a quick supply run. You're building a civilization in slow motion, with feedback loops measured in human generations. This affects the social and economic structure profoundly. The colony must be intensely focused on long-term planning and maintenance of existing capital. There is little room for disposable consumerism or rapid technological churn. Things are built to last centuries. Repairs are valued over replacement. This fosters a conservative, careful economic culture, but it also could stifle dynamism. Finally, the economic risk is absolute. A major failure, a reactor meltdown, a catastrophic habitat breach, could wipe out the entire investment. There is no bankruptcy protection 1 billion kilometers from home. The loss would be total, a sobering thought for any potential investor or government backer. In essence, the economics of Titan colonization ask humanity to make a multi-trillion-dollar, multi-century charitable investment with no financial return, betting that the scientific and existential payoffs are worth bankrupting other earthly endeavours. It asks for a permanent commitment to fund a distant sibling civilization that can give nothing material back. This is not a challenge of engineering alone, it is a challenge of human nature, priorities, and our ability to act as a species for a goal measured in centuries, not quarterly reports. The colony on Titan, therefore, would not be a business venture. It would be a statement, a cathedral built in ice and metal, its purpose not profit but knowledge and the perpetuation of life in a cold cosmos. And history tells us that building cathedrals requires either immense faith or immense empires. Whether 21st century humanity possesses either in sufficient quantity to reach the orange shores of Titan is the quiet, unspoken question underlying every technical discussion. The machinery might be possible, but the wallet and the will remain the most untested components of all. That cathedral, once built, cannot afford a single cracked tile and a single leaking pipe, or a single speck of dust out of place. Its sanctity depends on an idea that is foreign to our throwaway earthbound society, the complete and total eradication of waste. On Titan, there is no away. You cannot toss anything out. Every byproduct, every emission, every scrap is either a vital resource to be recaptured or a potential of poison that will accumulate and kill you. The management of waste and the drive for perfect recycling are not environmental virtues there. They are the absolute, non-negotiable mechanics of survival. Let's start with the most immediate loops, air and water. The breathable atmosphere inside the habitat is a carefully balanced mixture of oxygen and nitrogen. With every exhale, the colonist adds carbon dioxide and water vapour to that mix. The system must scrub the carbon dioxide relentlessly. On the International Space Station, this is done with systems like the Carbon Dioxide Removal Assembly, often using materials like zeolites to absorb the gas. On Titan, these systems would need to be far more robust, reliable, and with greater capacity for a larger population. The captured carbon dioxide isn't just waste, it becomes a feedstock. It can be combined with hydrogen from water electrolysis to produce methane and water through the Sabatier reaction, effectively recycling carbon and creating water. Or it could be fed to plants in the agricultural modules, which would convert it back into oxygen and biomass. Every molecule of carbon must be tracked and purposefully redirected. Water recycling is even more critical. The colony's water supply is a fixed amount with minor, difficult-to-replace reserves. Every drop of moisture from breath, sweat, urine, shower runoff, and farm transpiration must be captured, purified, and returned to the potable water tank. This involves a multi-stage process of filtration, chemical treatment, and likely distillation or reverse osmosis. The systems must achieve near 100% recovery. A loss rate of even 1% per day would deplete the reserves in a matter of months. The purification must also be flawless. A failure could introduce pathogens or toxins into the drinking water, causing illness or death in a closed community with limited medical resources. The technology for this exists, but on Titan it cannot fail, ever. This means multiple redundant systems running in parallel, with constant monitoring of water quality. Now, let's talk about solid waste, specifically human biological waste. This is not sewage to be treated and released, it is a treasure trove of nutrients. The feces and urine contain nitrogen, phosphorus, potassium, and other trace elements essential for plant growth in the hydroponic farms. Processing this waste safely is paramount. It would likely be first sterilised, perhaps through high-temperature composting or autoclaving, to kill any pathogens. Then, the solids could be composted or processed through anaerobic digesters to break them down into a stable, nutrient-rich fertiliser that can be dissolved into the hydroponic nutrient solutions. The urine, rich in nitrogen and water, would be processed separately to recover both the water and the nitrogen compounds. This closes the nutrient loop, food to human to waste to fertiliser to food again. Any inefficiency in this loop means you have to supplement with imported nutrients, which are finite. This turns the colony's toilets into mining stations for tomorrow's dinner. Beyond biological waste, there is the mundane trash of human life. Packaging materials, worn-out clothing, broken tools, food scraps not fit for recomposition. A true circular economy must be invented from scratch. Plastics would be designed from the start to be recyclable, likely sorted by type, shredded, melted, and re-extruded into new filament for 3D printers or moulded into new parts. Metals from any broken component would be salvaged, melted down, and reforged in small-scale foundries. Clothing would be repaired, repurposed, and ultimately recycled into insulation or other fibrous materials. The concept of single-use anything is a lethal extravagance. Even dust from air filters and the inevitable shed skin cells and hairs become part of the organic processing stream. Then we enter the more dangerous territory, industrial and chemical waste. A colony with any ambition will have workshops, laboratories, and eventually manufacturing. These processes will create waste products, spent solvents, metal shavings contaminated with cutting fluids, acidic or basic chemical byproducts, and waste from any local chemical processing of tholins or methane. On Earth, these are often treated and diluted into the environment. On Titan, there is no environment to safely absorb them. Dumping them outside would contaminate the very prebiotic chemistry you might be studying, and could potentially create a toxic zone around your habitat. Incineration is an option but requires oxygen, which is precious, and creates its own exhaust that must be scrubbed. The only sustainable path is to design every industrial process from the beginning to minimise waste and to have a plan for the utilisation or permanent safe storage of any byproduct. This might mean developing novel chemical pathways that turn one process's waste into another process's feedstock. For example, the acids produced in one reaction might be neutralised with bases from another, creating a safe salt that could be stored or even used as a mineral supplement. The storage of truly inert, non-recyclable waste becomes a logistical problem. You would need designated sealed storage volumes, constantly monitored, taking up precious space inside the pressurised habitat. Over centuries this could become a significant burden. The psychological dimension of this cannot be ignored. Living in a world where every bit of trash must be meticulously sorted, where your bodily waste is openly discussed as a community resource, and where a single act of littering could jeopardise a life support system, requires a profound cultural shift. The colonists must internalise an ethos of perfect citizenship where personal convenience is always subordinate to systemic purity. Children would be taught from birth that everything has a place and a purpose in the cycle. This level of enforced environmentalism is far beyond anything on Earth. The stakes of failure are what make this so intense. Imagine a scenario. A faulty valve in the water purification system allows a small amount of cleaning solvent to back-contaminate the potable water tank. Dozens of colonists become ill with chemical poisoning. The medical bay is overwhelmed. The contaminated water must be isolated and dumped, depleting reserves. The purification system must be taken offline for repairs. Suddenly, the colony is in a full-blown survival crisis, all from a tiny mechanical failure in the recycling chain. Or consider a more gradual failure, a slight inefficiency in the carbon dioxide scrubbers. Over weeks, the carbon dioxide level slowly and perceptibly rises. Colonists begin to suffer from chronic headaches, fatigue, and impaired judgment. Productivity drops, mistakes increase. The cause might be elusive until someone thinks to double-check the scrubber efficiency ratings. By then, the reduced cognitive function of the crew may have already led to other errors. This is why monitoring these systems is the colony's central nervous system. Control rooms would have real-time readouts of every major recycling loop: water purity, oxygen percentage, carbon dioxide levels, nutrient balances in the farm tanks. The data is as critical as the air itself. In the end, the Titan colony is the ultimate expression of a closed ecological system. It is a tiny, fragile bubble attempting to mimic Earth's grand, robust cycles on a minuscule scale. There is no river to carry waste to the sea, no atmosphere to dilute toxins, no soil to decompose and renew. The colonists must be the stewards of every atom, playing God to a miniature world where the sin of waste is punishable by death. Their entire civilization is a relentless act of balancing chemical equations, where the only acceptable answer is zero loss. It is a life of meticulous, unending housekeeping on a planetary scale, where the price of a messy room is the failure of a dream and the silence of a tomb 1 billion kilometres from home. That meticulous, closed-loop housekeeping is driven by a need for internal purity, but it collides head-on with an even larger external responsibility: the profound ethical duty to protect the alien world you have come to inhabit. Titan is not just a harsh environment, it is a unique scientific treasure, a frozen library of prebiotic chemistry, and possibly a window into how life begins. The very act of colonization threatens to burn that library down permanently. This creates an ethical dilemma of staggering proportions that would shape every single action the colonists take. The core of the issue is contamination, both forward and backward. Forward contamination is the risk of introducing Earth life to Titan. Backward contamination is the risk of bringing something from Titan back to Earth that could harm our biosphere. While less of a concern with Titan's cryogenic chemistry, forward contamination is the immediate, overwhelming problem. Think about what we bring with us. We are walking, talking ecosystems. Every human colonist is covered in and filled with billions of microbes. Our gut bacteria, skin flora, even the dormant spores in our clothing, these are all part of Earth's biosphere. On Earth, they are harmless or beneficial. On Titan, they would be invasive aliens. While it is extremely unlikely that any Earth microbe could metabolize and reproduce in the liquid methane lakes or the frozen Tholin plains, the possibility cannot be ruled out entirely for every niche. More pressingly, even if they die quickly, their dead organic remains and chemical signatures would contaminate the environment. They would become a layer of biological pollution over the pristine prebiotic chemistry, making it nearly impossible for scientists to determine what molecules are truly native to Titan and which are hitchhikers from Earth. A single unsterilized fingerprint on a sampling tool could ruin a decade of research. For a world that is essentially a giant natural laboratory for studying the chemical steps toward life, this is an existential threat to the very reason we went there in the first place. Therefore, the protocols for planetary protection would be draconian, far beyond anything used for Mars. Every piece of equipment landed on Titan would need to be sterilized to an unbelievable standard, likely using a combination of heat, radiation and chemical baths. But the humans themselves are the biggest contamination risk. You cannot sterilize a person. This means the colony must be a perfect biological containment facility. The habitat is not just a home, it is a quarantine zone. The airlocks are not just doors, they're decontamination chambers. Exiting the habitat would require suits that are surgically clean on the inside and meticulously scrubbed on the outside before each egress. Returning would involve multiple stages of decontamination. Perhaps a spray of reactive chemicals, a bath of ultraviolet light, and a vacuum cycle to remove any Titan dust. Any samples brought in from the outside would be treated as high-risk biohazards, examined in sealed glove boxes that are themselves under negative pressure. The colony's wastewater and waste processing systems would have to include a sterilization stage to ensure no Earth microbes escape through a leak. The psychological weight of this is immense. Every colonist is a potential vector for the destruction of the very science they are there to conduct. A moment of carelessness, a suit tear that isn't reported, a forgotten procedure, could have permanent consequences. This fosters a culture of extreme caution and constant vigilance, adding another layer of stress to daily life. The ethical tension deepens when we consider the long-term goal of the colony, to expand, to build, to become a permanent home. Human activity is inherently messy and transformative. Even with perfect protocols, our presence alters the environment. The heat from our reactors and habitats creates thermal plumes. Our mining and construction disturb the surface. Our mere foot traffic, even in suits, compacts and changes the landscape. Over decades and centuries, the area around the colony would become an undeniably human-altered zone. This leads to the central ethical question: do we have the right to do this? Titan is a world that has followed its own natural chemical path for billions of years. It represents a branch of planetary evolution separate from our own. By colonizing it, we're inevitably making it more like us, imprinting our biology and our technology onto it. We're effectively ending its independent story. Some would argue that Titan's scientific value is so supreme that it should be preserved as a wilderness area, studied only by sterilized robots, with human settlement forever forbidden. This is a powerful argument. The potential knowledge lost about the origins of organic complexity in the universe could be worth more to humanity in the long run than a single struggling outpost. Colonization from this view is an act of profound selfishness, sacrificing pure knowledge for the symbolic flag planting of a few. The counter-argument is that humanity's drive to live and grow beyond its cradle is also a profound part of our nature, and that the knowledge gained from sustained in situ human presence, engineering, medicine, sociology in an alien environment, is also invaluable. Furthermore, establishing a second home for humanity could be seen as an ultimate act of species preservation. But this pits two goods against each other: the preservation of a unique natural world versus the propagation of our own species. There is no easy answer. For the colonists on the ground, this ethical debate becomes practical policy. Their charter from Earth would likely designate large areas as wilderness preserves, off-limits to all but the most delicate robotic probes. Their own industrial activities would be constrained to a limited development zone. They would become park rangers and stewards of a world they're simultaneously trying to tame. This strange duality would define their identity. They are both the invaders and the protectors. Their daily mission would be split: survive, grow, but do not touch. This extends to the use of local resources. Processing tholins for manufacturing might be permitted, but only if done in a completely closed system that prevents any Earth chemicals from leaking out. Melting surface ice for water might be allowed only in designated areas, following strict environmental impact assessments. It is environmentalism taken to an interstellar scale, with the colonists as the regulated party. The ethical burden would be heaviest on the first generation, the ones who break the pristine silence. They would know they are the ones blurring the line. Future generations born there might see Titan less as a pristine lab and more as their home, to be used and managed, shifting the ethical framework over time. This cultural drift is inevitable and adds another layer to the colony's eventual separation from Earth. Earth's scientific community might continue to plead for absolute preservation, while the Titanians, struggling to build a civilization, might view those pleas as the distant, impractical demands of a planet that doesn't understand their struggle to survive. In the end, the ethics of colonizing Titan force us to define what we value most. Are we explorers who observe, or a species that spreads? Can we be both? The Titan colony becomes the test case. Its success or failure isn't just measured in its longevity, but in its ability to walk this impossibly fine line, to build a heartbeat in the silence without drowning out the whisper of the world they found, to add their own chapter to Titan's story without tearing out the ancient, frozen pages that came before. It is the ultimate test of whether we can grow up as a species, to leave our mark without leaving a stain, to become residents of a universe that does not belong to us, with the humility and responsibility that should entail. Every airlock cycle, every sample protocol, every decision to drill or not to drill is a vote in that ongoing ethical referendum, held 1 billion kilometres from the voting public, where the consequences are permanent and the silence of the orange haze offers no judgment, only consequence. That ethical referendum, conducted in silence over decades, underscores the most humbling truth of all. Colonizing Titan is not a project for our lifetimes, or even our children's lifetimes. It is a commitment measured in centuries, a horizon so distant it challenges the very way human societies think and plan. The journey from the first precarious landing to a truly self-sustaining, growing civilization on Titan is not a linear path. It is a slow, generational crawl, with each phase presenting its own monumental tasks and its own redefinition of what the colony even is. The first phase, spanning perhaps 50 to 100 years, would be the pioneer era. This is the period we've been mostly discussing. A small crew of scientist engineers living in landed modules, surviving on imported supplies and perfecting their recycling loops. Their work is pure survival science and foundational exploration. They conduct the first detailed surveys for resources, test construction methods with local ice, and begin the agonizingly slow process of building infrastructure. Every accomplishment is hard-won. A working water extraction plant that produces 10 litres a day is a cause for celebration. A new greenhouse module that adds 30% to the food supply is a revolution. The population might number only in the dozens. This society is necessarily authoritarian in a benign, technical sense. Decisions are made by consensus among experts focused on survival, with little room for debate or leisure. The psychological pressure is immense, and the cultural focus is entirely on the mission, on maintaining the fragile bubble. The second phase, perhaps a century in, could be called the consolidation era. The colony has survived its initial crises. It has a somewhat reliable, if limited, nuclear power source. Its water and air recycling are robust. It has mastered basic food production. The population has grown, maybe into the hundreds, through both new arrivals from Earth and the first native-born generation. Now, the focus shifts from mere survival to the beginnings of true industry. This is when the dream of using local resources starts to become tangible. A small chemical plant begins processing Tholin dust to extract carbon fibers and useful polymers. A machine shop, equipped with 3D printers using local and recycled materials, starts manufacturing simple replacement parts instead of relying on Earth shipments. The colony begins to look less like an outpost and more like a very sparse, very specialised industrial town. Social structures become more complex. With a larger population, you need more formal governance, perhaps a council elected from among the various technical disciplines. You need teachers for the children. You need planners who think beyond the next harvest to the next decade. The cultural identity begins to solidify. The stories of the founders become legend. Earth feels more distant, not just in miles, but in mindset. The third phase, entering the 2nd or 3rd century, is the self-sufficiency era. This is the make or break point. the colony must achieve the ability to manufacture all critical components for its own existence. Pressure vessel segments, reactor parts, advanced electronics and medical equipment. This requires a technological base that mirrors on a small scale the industrial revolution of Earth. It needs mining, refining, chemical synthesis and precision manufacturing, all adapted to Titan's conditions and using primarily local materials. This is a hurdle of staggering difficulty. It might require breakthroughs in automation and artificial intelligence to run these complex industries with a limited population. During this period, the colony's relationship with Earth undergoes its final transformation. Earth is no longer a lifeline, it is a trading partner, and a distant one at that. The colony might export unique data, perhaps even designs for technologies developed to survive on Titan, but materially the tie is cut. The colonists are on their own. This is when the cultural and even biological divergence becomes pronounced. The Titan-born generations, adapted physiologically to low gravity and psychologically to life under the dome, will see the universe differently. Their art, their social norms, their very language will evolve to reflect their reality. They might develop a timekeeping system based on Saturn's seasons or Titan's own rotation. Their concept of nature will be the orange haze and the ice caves, not forests and oceans. They are Titanians. The final speculative phase is the maturity era, centuries hence. Titan is a homeworld. It has multiple settlements, perhaps connected by subsurface tunnels or surface transit networks. It has its own culture, its own history, its own political dynamics, entirely separate from Earth's. It might even begin its own program of exploration, sending missions to other moons of Saturn or beyond. The original ethical constraints might have relaxed, or they might have hardened into a planetary religion of the environmental stewardship. Their relationship with Earth could range from warm alliance to cold indifference to outright conflict, depending on the political evolution of both worlds. The key takeaway is the timescale. Each of these phases requires a stable, continuous investment of resources and political will from an Earth that will itself be undergoing unimaginable changes. The colony must survive not just Titan's environment, but Earth's fickleness. Wars, economic collapses, and shifts in political ideology on Earth could sever the support at any point during the first 2 centuries, dooming the colony to a slow decline. This demands a new form of intergenerational pact, a promise from humanity to a future branch of itself that we will not abandon them halfway through their childhood. Furthermore, the colonists themselves must embrace a mindset where they work for a future they will never see. The pioneers plant trees whose fruit their great-grandchildren will eat. This long-termism must be baked into their culture from day one. It is the opposite of our modern short-term economic and political cycles. In practical terms, this means the colony's design must be inherently scalable and maintainable for centuries. Every system must be designed for easy repair and upgrade with local materials. Knowledge must be preserved meticulously, as the loss of a technical manual could set it back a critical industry for a generation. The social system must be resilient enough to avoid collapse from internal strife over such long periods. Ultimately, the horizon for Titan is not about overcoming a list of technical challenges. It is about sustaining a vision across time. It asks whether humanity can act as a coherent, patient species. Can we start a story that only our descendants, transformed by an alien sky, will get to finish? Colonizing Titan is not a mission. It is the founding of a lineage. The initial landing is not the climax, but the first word in a new history book. The true challenge is not the cold or the distance, but the patience and the faith to write that book, chapter by slow chapter, for hundreds of years in the dim light of an orange sun, trusting that the story and the storytellers will be worth the wait. The silence of Titan is not just a physical condition, it is the silence of a stage before the play begins, a play that will last for millennia, telling a tale not of Earth, but of what grows from Earth when it is planted in the most unlikely of soils.